before we can really dive into electricity and how it kind of functions within our universe, we have to understand a few basic things. So, in order to introduce you guys to electric charge, we'll go back and we'll take a look at the first civilization to really start to experiment with it and start to realize that there was a way to generate it and things along those lines. And that would be the ancient Greeks. And what they discovered a long time ago was that if they took pieces of amber and they rubbed it up and down on like rabbit fur or animal skin, they found that it kind of then possessed some interesting properties. They would kind of attract one another. You could get some of these static shocks when they did that, and that's really the first time that human civilization starts to realize that there's something that they can't see, but that is certainly present within our universe. The amber, the Greek referred to that as electrum, and that's actually where the term electricity comes from, electron, electric charge, because they originally, discovered that this material they called electrum seemed to be able to have these interesting properties that we know today as electricity. Before we can really dive into electricity and what it is, we do have to kind of go back very quickly and understand the general structure of the atom. And we have obviously the nucleus, which is the nucleus, which consists of the protons and the neutrons. Those are bound within the nucleus. And then there's those outer electron shells where the electrons, we've typically seen in chemistry, like the Bohr model, these electrons kind of orbiting the nucleus. The reality is quite a bit different. Probability clouds and some other crazy quantum things that even I have trouble wrapping my head around. But we're going to go with the basic model of the atom that we kind of know. So the nucleus binds the protons and the neutrons. They can't really move anywhere, and the electrons are in the outer shells, kind of swirling around. Because of the fact that the protons and neutrons are bound by the nucleus, it requires a lot of force and energy to actually remove those. That's where you have nuclear fission, nuclear fusion. Like when you want to mess with protons and neutrons, you need levels of energy and force associated with like atomic bombs. The electrons are not bound by the nucleus, so they require significantly less force, significantly less energy to remove them. That's part of the reason why they can kind of jump from atom to atom. Atoms can share them, but atoms are not typically under normal conditions sharing like protons, neutrons. Those are bound within the nucleus. All right, it's for that reason that the electrons are transferred under normal electrical interactions. So when we describe electricity, we're describing the movement of electrons. We're not describing the movement of protons and neutrons. For our purposes, we're going to assume that they are not going to leave the nucleus. They are just going to remain there. If a molecule or an atom gains or loses electrons, it can become more positive or negative as a result. If an atom gains or loses protons, it literally becomes a different element. So that's another reason why when we're discussing electricity, we're talking about the flow of electrons between molecules. We're not talking about molecules actually becoming other elements or other molecules. All right, so in terms of charge, now that we kind of have a basic understanding of charge, we have to realize that there's actually only two types of charge, not three. So every now and then people think there are three, but we have to be very careful about how we define one of them. So the first one would just be any object or particle that has more protons than electrons, or more positive charges than negative charges. That makes that object positively charged. In the other case, something could have more electrons than protons, more negative charges than positive charges, and therefore we say that that object has a negative electrical charge. Most people are probably with me so far. The third, which is not really a type of charge, is what we call neutral. That's when you have an equal number of positive and negative charges. That's the absence of charge. So even though we're listing three here, just realize there are two types of charge, positive and negative. Neutral is actually the absence of charge. Okay, there's no charge. The next thing we need to make sure we understand before we can move forward is how these charges interact with one another. And I do think most people have an innate understanding of this, but like charges, meaning the same, two positives, two negatives, they repel one another, as you can see in that diagram on the right. And opposite charges, like a positive and a negative, they will attract one another. So much like gravity is always attractive as far as we are aware of in our little section of the universe, uh, electrical charge can be either attractive or repulsive depending on whether you have the same, like, or opposite charges. The only other thing we really need to understand is how we measure it. What are the units of charge? And we measure charge in what are known as coulombs. 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 Now, one lightning bolt, your average lightning bolt, is between 1 and 10 coulombs, which tells you how extremely large a coulomb actually is. It's so large, in fact, that we are not going to be dealing with coulombs in most of what we look at. One coulomb is more than enough to kill a human being. So when we have our experiences in day-to-day life with static shocks, we're not talking about coulombs of charge. We need to come up with a prefix to represent smaller than 1 coulomb, and we typically use what's called the microcoulomb. So you've probably seen, we have seen that lambda symbol before with coefficient of friction. So if we use it as a variable, it's coefficient of friction. If we use it as a prefix, it means micro. And a micro just means 1 millionth. So 1 times 10 to the negative 6th. So when you see like 1 microcoulomb, we're talking about 1 times 10 to the negative 6th coulombs, or 1 millionth of a coulomb. There are some other prefixes we may experience, but micro is very common and you can use it with any unit. So a micrometer is 1 millionth of a meter. Micronewton, 1 millionth of a newton. But we're going to use it here with the coulomb prefix. To go one jump past that, the other thing we will be given, but we have to know how to utilize, is called the elementary charge. Elementary meaning like foundational, fundamental. The elementary charge is plus or minus 1.6 times 10 to the negative 19th coulombs. And that is quite simply the charge on either a proton or an electron. So every proton in our universe has a charge of 1.6 times 10 to the negative 19th coulombs, and every electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. All right, just to tell you how small that is 16 billionths of a billionth of 1 coulomb. So 16 billionths of a billionth of a coulomb. So an extremely small amount of charge, but the fact that every proton and every electron always carries this charge, the elementary charge, it allows us to do quite a few conversions and figure out exactly how many electrons are moving back and forth, which we'll see in a few examples as we move forward. The last thing you're going to want to realize is to determine that, to figure out how much charge is on an object, or to convert between the number of protons and electrons and the actual charge an object has, we're going to use the following calculation. It's really no different than if you wanted to figure out like how much something costs. So if you want 3 apples and they cost $1 a piece, it's $3. Well, instead of the number of apples and the cost of an apple and the total price, it's going to be the number of protons or electrons instead of, the number of apples or whatever you have. Instead of the cost of each of those, it's the charge on each of those, the elementary charge. And if I multiply those, I will get the total charge on that object. And in the subsequent videos, you will see a few examples of how we can use this equation, but make sure you have it written down. I know that was quite a bit, but you now have the basic building blocks for understanding electricity and electric charge, and we'll use those as we move forward to kind of show you in more and more ways and more in depth how all of this plays together to give us our understanding of electricity and electric charge.